Alright, so this video is on hypergeometric probability distributions. You have a model that's pretty complicated looking, but it's actually not too bad to work with. So you could read the blurb there: discrete probability distribution with k successes and draws without replacement, finite finite population size n contains exactly k objects with that feature, and so on. What we're going to look at, we're just going to go into a pretty brief example, and it's really the only type of problem you'd be responsible for when it comes to a test. So we're looking at this as kind of a subcategory situation where you have a group of individuals, but they could be divided by some sort of characteristic, and then we could determine probabilities for each group. Right, so the examples, suppose there are 50 officers, 10 female officers, and 40 male. Suppose 20 of them will be promoted. Let X represent the number of female promotions. And then they give you the whole formula and everything, but if we look at it closer, what we're determining here is the number of different, or the probability of the number of different possible promotion values that a female officer could have. So it spans from 0 to 1 all the way up to whatever the variable is. So you have male officers that could also be promoted. And so if you look at it and say, well, if 20 people are getting promoted and none of them were female, then 20 of them would have to have been male. Continuing on, if one of them was female, then 19 of them would have to be male. So the more females, the less males, and vice versa. The bottom gives us the total number of ways in which 20 people can be selected from a group of 50. Right? So it's really just sort of subcategorizing. There is a function built into the calculator that'll do this for you, but I've found that it's actually just easier to do it using the ordinary combinatorics menu in NumWorks. So if I wanted to create a table of all these possible values, I could do it one at a time, and it's really not that bad. I could also do it in a table, but let me just run you through this first calculation here. So I like to get the division bar in first. Even though I have to erase the ANS, I just find it to be easier in terms of constructing a fraction. So toolbox, go back, you'll see combinatorics. You have the n over k one, that's the combination. Right, so 10 over 0. Same deal for the rest of it. So 40 over 40 over 20 again, and then 50 over 20. All right, so again, that's in the first combination. You had 10 females, none of them were selected. You had 40 males, all 20 of the possible promotions were occupied by males, versus or divided by any of the 50 being accounted for in each group of 20. So running these numbers, you get a decimal. I could put it in my calculator. Put it in my table. I'll put the 0 first. 0.00292. Now, if I wanted to, this would be kind of a pain, but I could go in and I could change this 0 to a 1 and change the 20 to a 19 and get the second value. I did it, so I might as well include it. Could do it again. And if you're comfortable with this approach, it's fine. It's just we always run into the issue that, okay, well, there's only up to 10 for I. What if you could go up to 100, so then you'd be at it all day. So 0.108. But let me just show you a table way of doing it. So same kind of approach to what we did with geometric and binomial cases. I'm going to fill with a formula. There is no template for the one for this column here. We'll have to handle that as we go. But for 0 through 10, I could use this. That'll give me 1 to 10. And I could just subtract a 1 from there. and make that an 11. Oops, not 111. And then go on down the line, and I have 0 through 10, right? It's a small enough sample that if you wanted to just type the number 0 through 10, that's fine, right? So fill with formula in the next column. This one's going to be empty. I'm going to use my fraction tool. Put my combinations in there. I'll do it all in one shot, and then just run through with the numbers. So what they're saying here is that we're leaving the bottom part of the first combination, we're leaving that variable, right? But my variable's in V1, so I'll do Shift Alpha V1. Oops, I accidentally hit a 2 there. Then 40 on the top, and whatever was not in V1 is what I want here. So out of the 20 people, I would subtract whatever's in V1. And then my 50/20 in the bottom. Putting this in, hitting OK will give me all the values in one shot. But again, it wasn't that crazy of a set of computations, so you probably could have just done it all by hand and been all right with it. I mean, you probably not too thrilled that you have to do that many computations, but it's not insurmountable is what I'm saying. Just going to get these numbers in. All right, a couple more. The 1.7. That would go to 99 times 10 to the negative fifth, right? And by looking at this distribution, we see that there is kind of a hump in sort of towards the middle. That's what I would call the sweet spot, because if you have so many spots available, there's 20 spots available, and you have a pool of males and females, you would not expect all the hires to be male. You would not expect them all to be female. You'd expect them to be somewhere in the middle, but there is a balance point based off of the number of individuals, the candidate pool, if you will, that you're starting with, right? So you had twice as many males available. Actually, no, not even. It was, 40? Yeah, it was 4 times as many males available, so it's a larger candidate pool. So you would not necessarily expect it to be a 50-50 split, but you would expect the females to be represented in there somewhere. Now, it didn't ask us to do this, but I'm just going to take you to the graph real quick, do a quick histogram, and see that it has kind of a normal distribution feel to it. It's roughly symmetric, and it doesn't seem to have any outliers. Right? So all of this is sort of detailing the process that we just used, right? That being said, I mean, even though it's a complicated looking formula, it's still pretty much a straightforward idea. When you say, in this example, suppose there are 30 students, 20 male, 10 female, applying to the same college. College is only going to accept 10 students. What's the probability that 5 of them will be male and 5 of them will be female? So let's just focus, pick a category, it doesn't matter. We'll go female first, then male, just because that's how it was in the other example, and then all, right? So you have 30 students in all, and 10 of them are going to be accepted. So that's if there was no subcategorization at all, right? You have 30 people, 10 spots. How many ways can you get groups of 10 from the 30 to fill those spots? Right? Now, if we focus on the females, there are 10 of them available, and we want 5. And that's what it's saying here. For the males, there's 20 of them available. We also want 5. So this is just the same calculation, just a slightly different context, but even if we really think about it, it's not that different contextually. Right? So, like I said, I like to do my division first. Little fraction bar there. get all the ingredients in. Ten, 5, 20, oops, wrong button. 25 and 30, 10. All right. And a good way to know that you have your numbers in the right order, I'll call it the top row of the numerator. You see the 10 and the 20. That needs to add to the top row in the denominator. The bottom row in the numerator needs to add to the bottom row in the denominator. So if you have that set up in that sort of fashion, then odds are you did it right. So I'm going to hit OK, and we're looking at about 0.130.